like larger pipeline has gotten more and more people have been coming to us saying, hey, yeah, we're actually using this and we would like support and new features, and here's what we want. So that's been really exciting for us. A couple other things to note here are the features tab. This is kind of I play with this probably way too much, the wording and the icons and the images and things like that, but I do want to point out a couple things here. The one thing I've noticed from my recent talks, even in just the last couple weeks, is people really tend to grok this concept of treating the model, your machine learning or your AI model, with the actual runtime itself. So, this is something, and that's that square in the middle box right there with the Docker logo, and it's chomping up a bunch of these model types. So, yeah, right, just real quick, we support pretty much all the major model types. We even support raw Python and raw Java and raw C and of course R and Scikit and Spark models and TensorFlow and all kinds of good stuff. So, but one thing we've been realizing, and this is kind of well known, is hyperparameter tuning is super big. Of course, people are always trying to tweak models. And the learning rates and the decision tree, the depth of decision trees, and all that kind of business. One thing that they didn't realize they could do, or hadn't really gotten to this point yet, is that they could actually tweak the configuration of the runtime itself. And so this surfaces now that we're treating both the model and like this runtime as one packaged unit. So if we bounce over real quick, I'm going to jump to a second tab here. We actually released, I think it was last week, we released the version 1.3.0. And in here, it's pretty close to master. So if you end up on master, you should be okay. But this is the 1.3 stuff here. We actually have all the instructions here. So here's the CLI you can install. And I've gone through these instructions multiple times myself because I always forget the instructions. And so this is one of the reasons I document them, not just for you guys, but also for me personally when I'm building and tuning models on my own here. Let's see. We also split out the CLI for version 1.3 such that we actually have this concept of kind of standalone. And so actually, let me jump over and show, if I show the products here real quick. These are the, this is our first attempt to sort of build, commercial support and, so really take this from an open source project into something that can be deployed at many different places and have a bunch of engineers behind it, and we're working on funding and all that kind of stuff. The funding stuff's actually been fairly straightforward. So fortunately, we live in San Francisco and there's money flowing everywhere. So yeah, that part's been easy. But the community edition here on the right that has my picture, this is the traditional, if you click on that link, it's the Jupyter Lab notebook here, and actually added a few new notebooks to summarize the latest 1.3 stuff. So if you bounce over, if you log in, you have to register for this, but there's no money or anything. It's all free. You can take a look at, if you click files here, at the root, there's a README here saying, all bets are off. This is totally public. Don't upload anything sensitive. This is just a sandbox. Some emails if you want to contact us to upgrade to the standalone, and GPU support. We just switched over to a pretty large GPU cluster to power this Jupyter, this community edition. So we're working to get Kubernetes talking to GPUs and exposing it through here. So that'll be really exciting. We'll see a bunch of Bitcoin miners hopping on and trying to hack everything. So yeah, that's always fun, dealing with those guys. Also, we've got a bunch of new pipeline notebooks here that have the latest for 1.3, so you can see some of the command line stuff. Now we are working, of course, on building Jupyter support natively. This is something that we've been doing ongoing. In both a magic fashion, so imagine something like model-predict, and then giving it the model name and some sample data here, but for now, we're just gonna, right, like just using the actual CLI here, and then also you can curl. And let's see, what types do we have here? We've got Keras, Python, Scikit, TensorFlow. There's a bunch more examples that I haven't converted over. You can actually see some of that in the experimental thing down here. I pulled in this Keras stuff. This actually comes from that Francois guy directly, the creator of the Keras project. And you can go through and play with some of these. So that's cool to have these sample like notebooks here. And then, of course, our Pipeline GPU workshop. All the goodies are there. Okay, so that's the community edition. Oh, and so back to the CLI, we split it out into this sort of cluster concept. And that's, so that's the enterprise version, of course. And then there's the server. So, there's kind of a cluster and server, and you, right, like the way that you actually interact with Pipeline is you train a model, then you package the model into the appropriate runtime, if that's TensorFlow serving, if it's the new TensorRT just came out by the NVIDIA folks, so we're working on really getting that runtime integrated and placed onto these new GPUs that we have. So we'll be doing some performance testing there. And also we've introduced this concept of the ability to actually optimize your model, and that's going to come with the standalone. We'll probably do some simple optimizations for the community edition just to kind of show what's possible. But some of the things that we're doing here with the optimize are actually quite a bit of the stuff that we talk about in the actual GPU workshop. The ability to use to post-process your models and slim them down and do weight quantization and all kinds of other fun stuff. This is, let's see, what's this here? Is this doing? So something we realized during, right, like by doing these workshops is, and showing these things within TensorFlow, and right, like there's other optimization. There's this library called TPOT, TPOT, for it sort of works with Scikit, and it's a way to do hyperparameter tuning and some other optimization. So what we've realized is there's so many right, like sort of hidden gems that, but they're really, really low level, or they require, right, like quite a bit of configuration and systems knowledge and all this kind of stuff. And what we want to do is expose those to the data scientists directly, so that from Jupyter they can actually optimize the model and they can deploy experiments and have an unoptimized versus an optimized, right? And you can optimize both the model and the actual runtime, like I said. So we can pin, for example, we can create a 3-part or right, like one full. Yes, let me show it here. I've got a good visualization. Features. So for example, if I zoom in here, this would be an experiment of 3 different models, but like we could actually choose GPU versus CPU for the runtime. We could choose TensorFlow serving. We can choose TensorRT. So it's in kind of, this is the one I'm like looking at here. And so when you upload, what you're uploading is not just the actual model itself, but some sort of indication of which runtime or which right, like chip that you want to deploy on. If you have access to the like Google TPUs, will certainly do those also if you're running on Google. And so keep in mind too that this stuff does deploy in your own VPC. That's this very last feature here at the bottom, kind of dangling. It's secure private hosting, so you actually pull this into your like private data center on premise, if that's Google Cloud, Azure, whatever. We have customers across the board. So we operate at the Docker level. The implementation detail just happens to be Kubernetes. That's what we choose, but yeah, we don't expose that stuff like necessarily to when you really pull this down. So that's all hidden from you. Okay. So, and then the last thing that we're really focused on, and hopefully we'll hit for the 1.4 release by the end of the year, is this concept of distributed training. So this is kind of the holy grail in particular for TensorFlow itself. Not a lot of people have gotten TensorFlow distributed training to work, not smoothly anyway, not like without a lot of hoops and a lot of installs and reinstalls and using Mesos and like all kinds of stuff. So, right, like again, we're trying to make this super easy for the data scientist to use and spin up a cluster. And so the goal here is from one command line argument, or from one execution of the command line, you can actually, this will package up the Docker images, this will split out the work, this will then it will allocate it onto the cluster. So there's a clustered version as well here. This is only showing standalone, which is single node, but right, like we're definitely focused on getting distributed TensorFlow working in a very easy way. So that's the other thing here. We got lots of examples. This one happens to be the MNIST stuff. Here, this is one other thing I had added to, and this comes from pretty much really everyone that's been using Pipeline has been asking, all right, this is cool. Here's, yes, I see the examples, but what's going on here? So we actually took one of the more complicated ones. This is TensorFlow that uses TensorFlow serving. We've broken down this actual predict Python script. This is what actually defines this sole predict method here. Now, there's a bunch of other stuff, and so again, I'm labeling things optional. This seems complex. You can make it as simple or as complex as you want. You really only need just this predict method. And actually, I keep meaning to highlight that this is kind of the full version here of like all the capabilities. But I'm going to very quickly show just like a super simple version here, which is just a couple lines. It's just literally you have to implement this predict method. Here's some other things here. These are all optional, but the more that you monitor, right, so the more instrumentation that you add to your code, the better charts you'll have and visualizations, and you can actually debug and see where time is being spent. So the more of these monitors that you add in there at various parts of your code, they will automatically show up and there's ways to get to these metrics, which I could show here in a sec. So, which makes the ops guys happy, because when you give a group, this standalone server or standalone cluster, they want ways to kind of poke it and see the logs and see the metrics and get in there, but not necessarily have to understand the details of Kubernetes or really have to debug all that stuff, for example. So we definitely have ways to get in there because, again, we're developers and ops folks ourselves, and we need ways to get in and see our own like models that we're serving up. So here's kind of the general flow. You do server build, boom, you give it the type, you give it. Now, this type actually is the hint as to which like runtime you should use. So if this is TensorFlow, it's going to wrap it in TensorFlow serving. If you put TensorRT in here, which actually we haven't released yet, it would then wrap it inside of the NVIDIA TensorRT specifically for GPU. What else? Here's the model path, which is, all of this should be relative to this. If you clone this repo, which I believe is the very first step, here it is right here. When you clone that repo, then all the models and all the examples are here. So these are the command line models, the ones that are in Jupyter Hub. We've converted, or inside of Community, we've converted over to work. Oops, let me get to this within the notebook itself. All right, and then scrolling down here. So this is a breakdown of what you would actually have to implement. Sorry, I keep scrolling here. If you click into models, this will show you different examples. You can go right to the type of model that you're most likely working with. You can write straight Python code if that's the case. You could, and if you have pickled models and that kind of thing, just go here, follow this pattern, clone this, copy, create your own model, and you should be off to the races here. All right, one other thing. So here's the actual prediction. Here's the command line prediction. This is doing it locally. There's a way to do like a little mini load test locally as well too. You can give it this final argument here. Well, it looks like I have to add that, but you can pass in, oh yes, here it is. Predict 100 predictions, and it's this test request concurrency. If you add that, it will do like a little mini load test locally on this model that you've packaged up with the runtime. And so this is the way where you could sort of gauge, even before pushing it out to production or out to the test environment, if these particular hyperparameters or the runtime configs have actually made a difference. So you can like sort of get the intuition right away, even just physically on your like local laptop. Which goes quite a long way. Also, the other benefit to this, packaging this up, the actual runtime and the model, is that there's no surprises when you go to push it out into the test environment, into production. You have the exact same libraries of scikit or TensorFlow or like whatever that you chose. And if I scroll back up here real quick and go, I can show you an example. If I click into scikit, you can look at pipeline conda environment here. And this is, so of course we're using conda very heavily. Something we heard over and over from like various customers, that they want to have full like control over which channels that they pull from. Here it's like conda forge. There's pip install capabilities. This is some of the pipeline runtime stuff that is given to you for free that gives you access to things like monitor and log, ways to get data out of this Docker container. Like I was talking about before, these ops guys want to get to things, so we give you this pipeline-runtime. That's all like fully open source. That's all out on PyPy, and you can pull those in and expose those metrics or those logs. Here you have, and so here, this is where you're actually pinning it to a particular version of scikit, pinning particular pandas, NumPy, all that kind of stuff. You can even pull in the MKL stuff by Intel, and off you go. So let's see, scrolling down again. So here we're doing a curl command. This is the exact same. So here we're using the command line and giving it this test request path, and I'm not going to keep scrolling up and down, but if you go back to that model subdirectory there within this repo, every model has this test request JSON, and this is just a convention that we've chosen, and you can also copy and paste that directly and do a curl. There's also Kafka support as well too. You could literally drop in the same Python predict method or this pipeline_predict full like module into your Kafka stream code. So similar to Spark streaming, Kafka streams. Yeah, actually, you could pull it into Spark streaming also if you're using PySpark and actually make predictions on a stream as data is coming in. Right? Yeah, so we prefer Kafka streams just because we know it very well, and there's one less cluster to have to deal with, and that's been surprisingly getting us quite a long way since we see tons of like Kafka support throughout these enterprises that we're targeting. So here's the curl command right there. Once again, this is calling locally. When you do push this out into your own cluster or like your own standalone server, your own Amazon server, then you would like replace that URL and the port with like whatever you've chosen. So what we're showing here, this is all 100% open source, so you guys can take it and like do with it what you want. One other cool thing that we expose is this REST endpoint for WebSockets. So you can actually tap into the live stream as data is coming along, and you can see how physically what are these three different models that's part of this experiment. What are they physically predicting? So here's the input, which is the 2, and then here's the output, which is the confidence of each digit, right? So in this case, I just literally copied and pasted the same one over, so like you're not going to see any differences. But if you do have a fixed experiment with these three models, you would actually see live, right, like what they're predicting. And what we're doing also, this is hidden behind the scenes, and this is actually part of the like sort of larger enterprise edition, is we're passing the same input to the other two models in a shadowed mode. So you can either split the traffic, so you have 98% going to model 1, and then 1%, and then 1% for those like remaining two models, Or you just have all the traffic go to the first model, which is the control model that you're right, like potentially comparing with, and then you would shadow off a portion of the traffic, sample traffic, to the other two. And of course, we're using Kafka beneath the covers. And instead of those second and third models that are responding on like REST API, we're actually passing them in through Kafka, and right, like, yeah, so reusing that same feature that I was just speaking about with pipeline_predict behind a Kafka stream. And then what we're doing is then logging, and we can compare, and I'll show a chart here in a sec how we actually compare those. But one other thing to show is that we have a layer on top of all of these predictions that's monitoring throughput. One of the features of the advanced editions are we actually show cost per prediction, because we know the type of physical instance, right, that we are on. And so we can estimate, right, like throughout the day, how much is each prediction costing. And that's cool, because when you go from, if, like, for example, you lose the Amazon Spot instances throughout the day, you can shift traffic over to the now cheaper Google instances, for example, or even across over to like Azure, right? So again, these are enterprise features that, and then, so yeah, one other thing here, this is all part of the open source here, is that you can actually look and see where is time being spent. Here, for example, I showed earlier in the code, if we scroll up, I'll try to do it slowly to not freak you guys out. We have 3 different monitors here, and this is on purpose. We are labeling, this is the transform_request, and physically the string that is placed here shows up in the metrics, and we can see where's time being spent. So with any request that comes in, we have to convert from the native request, if it's JSON, if it's Avro, whatever's coming in. We then have to call the prediction on that like transformed like request, and then when we get the prediction value, if it's in TensorFlow, for example, we have to convert that tensor back into like JSON, or right, to like generate the response type that's needed. And since I'm up here, actually, here's the start. So once you package and build it up with the runtime, you can then start it. You can then also take a look at the logs, and then this is where we actually do the predict. So let's see. Yeah, so this is showing the throughput, and if there's any like fallbacks or circuit breakers that right, like you want to set up, these will like show up here too. If your service is getting saturated to the point where it can't handle it, it'll this layer that sits on top of all the predictions will actually flip a circuit and can send back fallbacks, like generic JSON response. If you're doing something like recommendations, you would just return the top 10 movies of all time, for example. Okay, so back to the detailed like prediction metrics here. So if you recall, we had those 3 monitors, and here they are showing up. The one on top is just kind of overall requests per second, and should, in general, match what's happening here at this higher level. Might be off by a tiny bit. And just, so transform request, transform response, and then predict. So we see that, in this case, the predict is actually dominating the workload, which is what we want. We've seen cases initially when we didn't have this level of detail, where we just saw this sort of overall, the 24 milliseconds from up here, and for the 99.5 percentile here, and we just assumed sort of incorrectly that it was the model. When really, when we first turned these on, we actually saw the transform request actually dominating, which is this thing in green, which is that tiny bar down here. What had happened was when the person had implemented their transformer to go from the native JSON, or I think it was CSV, into TensorFlow's tensor, they had or I think into NumPy, because yeah, TensorFlow speaks NumPy pretty well. They had used a suboptimal library to make that conversion. They had chosen a I think it was the Pandas CSV, which is optimized for more batch, whereas this was like a whole bunch of small requests coming in. And so we actually, when we turn this on, because the yeah, so this particular data scientist kept changing the model, and which was just affecting this predict. And this predict wasn't, really making any difference with the changes that they were making. Yes, even though we thought it would make huge changes and speed ups, but it really wasn't. And it's because when we, at the same time we were building out this feature, this is a few months ago now, but when we actually turned this on, we saw transform request was dominating the workload, and actually predict was not that bad. So we've since tuned it, and now this is an example where transform request, transform response are as small as they can be, and then where we thought the slowdown should be is in this predict method, and this is what's actually calling, going through the neural network and really going through all the layers and coming up with a prediction. So there's some instructions on how to get it working there. You can stop the server too. And so all of this depends on you having, Docker for Mac installed, Docker for Windows. We really do everything at the Docker level. That was one of the reasons PipelineAI actually started, was we finally had a stable Docker for Mac and sort of a local like Docker environment that didn't depend on like VirtualBox and all these goofy tools that required a lot of like network knowledge and had a whole huge support surface area. So once Docker for Mac came out, and then once Kubernetes sort of became popular and started to and really more tools started to hop onto Kubernetes that give us like the intelligent routing and the ability to do canaries and split traffic into 98%, 1%, 1%, and to do traffic shifting traffic shadowing, right? Like these tools on top of Kubernetes really launched Pipeline, and then really sort of opened up a whole lot of use cases for us. Let's see. So yeah, this is kind of the value add stuff. We've got this fun, slick drag and drop where you can actually take a model or Docker image and drop it, locally, and this will take it all the way as far as you want. If your managers, for example, or your VPs or directors will let you take it all the way to production, we can certainly do that. In most cases, we see people take this to the test environment right before production, and then they've got production data being shadowed into their test environment. So that's kind of the most common thing. Coming from Netflix, right? A few of us actually prefer to push it into production directly. That way, we don't have a separate test environment that we have to maintain, and that falls behind. And because we experiment safely in production on tiny bit of traffic or shadowed traffic where it doesn't affect production at all, we're totally comfortable pushing these experiments directly into prod. That's not always the case, of course. So we support the other so getting it right before production. So here's some other benefits. Here's the optimization stuff. This comes directly out of what we do in the GPU workshop, which if I bounce over a tab here, I actually added this workshops tab. This now has more info on, I think we've got a couple coming up in one in Dublin, and that's timed with the Spark Summit, and I believe there's another one in November, I think, for the West Coast of the US. Okay, so these are some of the optimizations. So you would essentially drag and drop. There's going to be like another drag and drop kind of thing, or from the command line, you would say optimize model, and possibly give it a hint. Tell it to use Teapot, or tell it to use TensorRT for the actual runtimes, or just use TensorFlow's sort of native capabilities, which we're exposing and making these accessible. Right now, these have to be built from TensorFlow source. When you use GPUs, you have to turn on a whole bunch of flags, which isn't ideal. This is not stuff data scientists should have to be burdened with. This is something that should just be a command line or something that they can do from the Jupyter Notebook itself. So some of these optimizations take a bit of time. So similar to when you deploy and you drag and drop and then slowly get a status or go to some status page and see where the process is, right? So that's definitely going to be exposed here. Also, there's some kind of low-hanging fruit things you can do. You could take your Spark ML decision trees and convert them into Java code. this is fairly straightforward stuff. You can actually get it down to C++, and if you're really crazy, you could actually create CUDA kernels from these things. We've seen a lot of different optimizations. So there's a whole separate side project kind of team that's been formed around this group within Pipeline and focused on the optimizations. And so the other team that we've spun up sort of out of necessity and from the use cases that we're seeing is this distributed training and the ability to train and deploy kind of with just a couple clicks and get some really good insight. So we've got quite a bit of work going on. TensorBoard, we tend to reuse this pretty heavily. Google has spent a lot of time investing in exposing these sort of training time metrics and how much memory is being utilized and CPU and GPU and that kind of thing. So we are not shying away from TensorBoard. In fact, we are starting to rely on it more and more and just sort of indexing things to get to these things quickly, these specific metrics. TensorBoard by itself is very file-based driven and sort of an append-only type mode. So it tends to slow down when you have a lot of metrics that you're logging. And so we've got tools that actually index that stuff, and you can very quickly pull up 2 of these training runs and then compare them. That's what's going on here, showing CPU utilization. Actually, we have GPU utilization here too, but it's not listed. Here's some of the resident memory. Also, as part of this is the enterprise stuff now that we're getting into is continuously deploying models. And this is a view of a Kubernetes cluster that just happens to be the details, but you could very quickly go to one screen and see how many prediction servers for TensorFlow do you have running, how many this is actually showing a lot of the training side stuff as well too, like Spark and Spark workers and SQL and that kind of stuff. But this is kind of the main dashboard that we show. So there's 2 base tenets with Pipeline. The first one is being able to package the model with the runtime and to hyperparameter tune based on both offline characteristics and online characteristics, right? So offline metrics being things like training accuracy, validation accuracy. This is stuff that we're very familiar with. We can very quickly just sort and say, give me the model with the best validation accuracy. This means it's not overfitting, things like that. And boom, this is the one we would choose. The problem is you can have a model at batch training time that is 5,000 layers deep, a huge deep neural network that is going to blow away one that's only 5 layers deep. And so by blow away, I mean it's going to have much, much better validation accuracy, much better training accuracy. The problem is when you come down to the real-time prediction side of things, when you're actually trying to serve these predictions, the response time for the 5,000 layer deep model is going to be in the tens of seconds, for example, versus in tens of milliseconds. And so this is an example of an experiment that we did where we were able to choose very easily which model wins offline. So the current model A is what we're trying to beat. The purpose of this experiment was to find a model that could predict similarly have similar sort of offline characteristics, but also can track and make similar predictions online. And so that's the sort of middle chart there, but also has, hopefully faster response time, right? So again, said differently, what we're trying to do is find a model that is faster to make the prediction, to make the forward propagation through neural network or just a simple scikit-learn prediction, but is not wildly predicting out of tolerance, for example. So here's a case where so C wins offline, and then when we pin it up against the current model A and this new model B, Model C actually tracks pretty well with the current Model A. And so what this chart is this is for the same inputs, for the same features. How are the actual predictions? And which prediction, and B seems to be predicting way out of tolerance, right? Right. Yeah. So whether or not B is faster doesn't really matter at this point because it's actually predicting way, way off from the current Model A. And because we're dealing with unlabeled data and so offline, it's all labeled data. It's all supervised training. We can, we can calculate the accuracy. With this middle bar, we're actually calculating precision. So model precision relative to the current model. And C seems to be tracking very precisely with A, so this is a winner. But now there's what we're really going for here is this last section, which is showing, pardon me, how did I get into the, okay. Yeah, this last section here that's showing the physical response time. So we see 17 milliseconds for Model C versus 28 milliseconds for Model A for the 99.5 percentile. This is great. We also see actually so traffic is starting to shift over. And this is something I haven't mentioned yet, but we're using bandits behind the scenes to sort of automatically optimize and dynamically shift traffic from the current model to the winning model. And so this way, throughout the lifetime of this experiment, which might be if we're doing 2 weeks or even 72 hours, if we didn't sort of dynamically shift, which is totally possible to just not do that and to just sort of analyze the results and then tear it down. But here we've chosen to actually start to shift traffic over. So it's pretty clear that C is the winner in both offline and tracking, and is 10 I think like 11 milliseconds faster than the current model. So it's pretty clear C is the winner, and so we can start to shift traffic over. So yeah, that's pretty powerful. Here's also a screenshot for our cost per prediction. It's an extension of what we're seeing here, except if you notice 0.0003. So we're pinning here not just the runtime, which would be TensorFlow serving or TensorRT or Scikit or the JVM, JPMML, whatever. But here we're actually comparing cloud. So it's not just the runtime that's packaged up inside of the Docker container, but it's physically where is this stuff running. And here's a case where for cost per prediction, which is what pretty much everyone uniformly says is something that they would like to see. In this particular case, at this particular time of day, we've lost all of our spot instances. Everyone in California woke up. All the developers woke up. It's 10 a.m. They all spin up. And all the other places around the world lose their spot instances. And so now it's actually cheaper on Google Cloud. And this is actually comparing an 8-core 50 gig or 60 gig instance on Amazon to a similarly spec'd out instance on Google Cloud. I think it's R32XL on Amazon and a N18 high mem on the Google Cloud platform. So these are very similar. You see the price is about a third. So this isn't always the case, but in this particular experiment, that's what was happening. And so similarly, we could start to shift traffic over. This is showing shifting traffic based on the model performance, which is what we actually saw up here. And now we can also shift traffic based on the cheapest cloud. This is one final thing that we really seem to like, and people get excited about this because it's tangible. We can, because we're tapping into specifically if I scroll up, because we're tapping in and sampling from both the inputs and the outputs for all three models, we can start to identify non-confident predictions, right? So one thing that we get or we are capable of tracking is not just the actual prediction, but the confidence. So if I scroll up here to make you guys crazy, here we show the confidence. And if, for example, so the digit that's being passed in is 2. If this particular model was giving us 0.1, 0.1, 0.1, and 10 0.1s, meaning it's not confident, and if maybe one of them is slightly better, that's the one we'll choose. These kind of predictions will get sent off into a separate Kafka topic. That's just the implementation detail here, but right, like logically, we're sort of isolating or quarantining those predictions. Now we're still returning the prediction, but we're just quarantining the right, like these particular unconfident predictions so that we can start to address them offline. And so this is a case where we've actually got Slack set up, and we've got Slack pulling from this like Kafka topic throughout the day, and it's just sampling, so it's not overwhelming. And there's dials to turn on the like percentage of, or the like sample percent and things like that. But so yeah, here's a case where it's pretty much the exact same image. We just added a little bit more ketchup. This is actually a real experiment that we did here, and each of these came back 51%, 49, and 49, 51. So these are within a particular tolerance that is identified as unconfident. And these show up, and now we can actually crowdsource. You can start to do it just sort of internally if you're not comfortable, making this public, or like giving it to Mechanical Turk or to someone like Crowdflower. So like throughout the day, you can have your like data science team or people within your organization, the like larger organization, and this sort of gamifies, right? There's like a leaderboard too that like you can set up and see, who's like corrected the most, or made the most impact. And here, so right, like what we're actually doing, if you step back, is we're taking previously unlabeled data and we're now labeling it. And this is right along the edges of these like borders, right? These sort of classification borders. And this is right where we want to be when we're like creating new training data. And so every time someone goes in here and clicks, there's some different strategies you can employ, like maybe one particular click like doesn't matter, but once 3 people see the same image and all click the same thing, right? Like then yeah, so this data now becomes like labeled data that gets fed in, and we're continuously training this model. And then yeah, so you could set up the model to be continuously deployed as well too. Or you could sort of do it offline, train it, and then push it out every night or every week, or and it will now be trained with this newly labeled data. So we're like highlighting specific data that is not confident. We're labeling it and making this model better. And this is something people get really excited about because they feel like they're actually contributing to the performance of this model. All right, so that's that. You can check out the examples here. I want to point out, I think we covered everything there. And the features, products I showed you guys. The big difference here is Community Edition. This is free. Something is speaking in German to me here. Not quite sure what that is. This is a case where, yeah, so this is Community Edition. This is us hosting it. This is public. Don't put anything sensitive here. It's got kind of bare bones Kafka, bare bones deployments with the command line. You can, pretty soon, we'll be adding to the Amazon Marketplace, the Docker Store, the Google Marketplace, and the Azure Marketplace. We'll have images you can pull down and actually do things a little bit more formal, and of course privately inside of your own data center or your own cloud. We have Enterprise Edition, which will give you some of this advanced traffic shifting and traffic shadowing and all that kind of good stuff. Also has the enterprise support, has the bandit tests, yeah, these bandit-based experiments, gives you continuous deployment, also gives you hooks into enterprise logging and dashboards if you're currently using Datadog, or have your own Kafka cluster, of course, we will tie right into that. So also supports auto-scaling, based on really different metrics that you provide, and we can actually auto-scale across clouds as well too. That's a feature of Kubernetes. Again, that's hidden from you. Just as long as you have all the right security set up between the like various public clouds, then yeah, so we can shift traffic there pretty easily. Another tab, we have integrations here. This is all pretty basic. We can integrate, because we have a REST API and we have a CLI and we support streams, we can, pop in and out of each of these tools here pretty easily. About us, yeah, it's just some fun stuff here. And then workshop, yeah, so sign up for that. Also docs, this is everything I was talking about before. Advanced Spark TensorFlow meetup. I've got the YouTube channel and ton of presentations here. I'm actually in the process of uploading the latest one from the London conference, the Open Data Source conference from just a couple days ago. So I think that's it for me here. Checking. Let me check the chat here, see if there's anything. Yeah, so please post questions here. We've got a couple minutes left. I think Brent is probably going to have to bounce off here in a bit. Yeah, I know he has a meeting here in a sec, so unfortunately I didn't leave him too much time. And okay, if there's no other questions or comments here, I'm going to wrap it up. I encourage you guys to check this stuff out, play with it. You can create tickets for us at help@pipeline.ai. Just post that in here. Post any follow-up questions to help@pipeline.ai. We love the feedback, and if you do get a chance, hop on one of the workshops. And we've priced it super low, so it covers the cost of the GPU basically. And yeah, so everyone gets a GPU here, which is really exciting for these workshops. And we actually have access to the new P100s on Google. So we'll be using the new chips by Google. And we've got these workshops nailed down pretty well. So I think there's a lot of value from these things. And yeah, let us know. We've got, I think it's upgrade@pipeline.ai is the email you can send us, and we'll get back to you if you guys want to upgrade to one of the, right, like basically become an early beta person for standalone and for enterprise. So I think that's it. Hopefully you guys found that valuable, and shoot us follow-up questions, and we will see you soon. We'll see you in about 4 weeks. Thanks.